Most general aviation aircraft are powered by simple air-cooled piston engines. The engine drives a propeller which provides the thrust to pull the plane through the air. The majority of engines in Western aircraft are currently made by one of two manufacturers, Teledyne Continental Motors or Textron Lycoming. Their products are very similar in layout and construction, with typically 4, 6 or 8 cylinders located opposite one another in a flat arrangement. They are normally air-cooled and are simple in their construction, some of the basic designs dating back to the 1940s. If cared for, the engines are reliable, and most are designed to have a time between overhaul, commonly referred to as a TBO, of 2,000 hours operation. Certain engines differ in their detail. Some have a turbocharger, which helps improve power at altitude. Others may have a gearbox at the front of the engine to reduce the speed of the propeller, but in general, the designs are the same. The whole purpose of an aircraft engine is to turn the propeller. It achieves this by taking in fuel and air and converting them into energy in order to rotate a shaft connected to the propeller. Inside the engine, this rotating shaft, known as the crankshaft, is connected to the pistons which slide up and down within each cylinder. At the start of the cycle, the inlet valve opens. The downward movement of the piston draws fuel and air in through the inlet valve to fill the cylinder. As the piston reaches the bottom of its travel, the inlet valve shuts and the piston starts to rise. This compresses the fuel and air. As the piston reaches the top of its motion, the fuel and air are highly compressed. At this point, the spark plug ignites the fuel and the mixture starts to burn. The rapid expansion of the burning fuel pushes the piston down, providing the force to turn the crankshaft in the center of the engine. The force exerted on the piston by the burning fuel creates the power to drive the propeller. After the fuel has been burned, the exhaust gas needs to be removed from the engine. As the piston rises, a second valve, the exhaust valve, opens at the top of the cylinder. The rising piston pushes the exhaust gas out through the exhaust valve and out of the engine. When the piston reaches the top of its movement, the exhaust valve closes, followed closely by the inlet valve opening once more. The piston then continues back down to draw fresh fuel and air into the cylinder, and the cycle repeats. This cycle happens continually as the engine runs, drawing fuel and air into the engine, compressing it, burning it, forcing the piston to move and make the crankshaft rotate, and then exhausting the burned gas, commonly referred to as suck, squeeze, bang, blow. If more cylinders are added to the engine, power can be increased and the power pulses evened out for smoother running. When an engine is stopped, oil gradually drains to the bottom and continues to do so as the unit remains idle. If an engine remains unused for long periods, then corrosion can become a serious issue. Products such as Aeroshell Oil W15W50 or Aeroshell Oil W100 Plus are designed to address the problem, as both contain a corrosion inhibitor. The speed at which oil will circulate when an engine starts is significant in the prevention of damage. This means that the correct oil needs to be selected for the aircraft's operational climate. Aviation oils tend to be classified by viscosity type: Aeroshell Oil W80, W100, and so on. The higher the number, the more viscous or thick an oil is. It is beneficial to use a thick oil in hot climates, as the high temperatures make lighter oils too thin to lubricate the engine properly during normal running. But in colder climates, thick oils will flow too slowly when an engine is first started. In this instance, the oil should be changed for one with a lower viscosity. The key thing to remember is that with single-grade oils, the viscosity must be matched to the climate. Thick oils in warm climates, thin oils for cold. Multigrades, such as Aeroshell Oil W15W50, have the advantage of being fluid at low temperature and yet give good protection at high temperature and can therefore be used in any climate. At low temperatures, Aeroshell Oil W15W50 has the best low temperature flow of any oil on the market and is the first choice recommendation for very cold climates. Let's now follow the path the oil takes when an engine is started and look at some of the problems associated with poor oil circulation. The journey of the oil starts at the reservoir in the bottom or sump of an engine. It's drawn up towards the oil pump, passes through the pump and on into the filter. The oil, now under pressure, fills the filter before entering a maze of passageways, known as oil galleries, from where it's directed to the main engine bearings. Once the oil has passed through the main engine bearings, it emerges into the center of the engine, where it's allowed to splash onto the cylinder, pistons and camshaft before draining back to the bottom of the engine. The camshaft has a vital role within the engine, controlling the opening and closing of the inlet and exhaust valves in the combustion cycle. The shape of the camshaft has been designed to operate against a follower. The follower then moves a rod connected to a rocker mechanism to allow each valve to open and close. Because the camshaft is one of the last areas to receive a fresh oil supply when the engine is started, it is not uncommon for it to suffer damage due to poor lubrication. Camshaft failure is one of the main reasons these types of engines fail to reach their designed overhaul life. When engineers investigate this type of problem, the telltale signs are clearly visible: wear on the cam profiles and pitting on the followers. The key to preventing such damage is to ensure that the correct oil grade is used for the climate. If an oil is too thick or too thin, then cam damage may result. Once the oil grade is correct, frequent use of the engine, at least once every 2 weeks, will also help. This ensures that the key parts remain coated with oil, protecting the engine between flights. If an aircraft is not used frequently, as is typical with private flyers, then elements can become dry. A lack of oil when the engine is first started can lead to metal-on-metal contact between the cam and follower, which can damage both. With infrequently used engines, additives can help. Shell blends an anti-scuffing additive into the multigrade Aeroshell Oil W15W50 and the single-grade Aeroshell W100+. This works by depositing the additive onto the metal surfaces so that the moving parts are protected from damage, even before fresh oil reaches them. In addition, both of these oils contain a corrosion inhibitor, which reduces the problem of rusting when the engine is not in use. You will also notice that parts of the camshaft are coated in copper. This is used in the manufacturing process of the cam, but can subsequently be a problem for the oil. Copper is a catalyst, encouraging the oil to degrade quicker than would be the case if it were not present. To overcome this problem, Shell Aviation blends yet another additive into Aeroshell Oil W15W50 and Aeroshell W100+. This additive, known as a metal deactivator, helps to protect the oil from the catalytic effect of the copper and keeps the oil in good condition throughout its life. Now that we have seen what is important inside the engine, let's look at the parts that are significant for us on the outside. Let's carry out an oil change. First, the oil sump plug is removed and the old oil drained from the engine. Next, the oil filter is removed and replaced. Once the new oil filter is attached and the sump plug put back into the engine, the fresh oil of the correct grade can be topped up through the fill point. The fill point also contains a dipstick to allow regular monitoring of the oil level in the engine. The aircraft is now ready to return to service, safe in the knowledge that Aeroshell Oils are looking after the engine.